Bernhard, go ahead.
All right, Tony, thank you. So, second part. So this is the one that we've all been waiting for, I think, the gravitational waves. So what can the gravitational waves actually teach us about the what's going on in the interior of core collapse supernova explosions? So the plan here will basically be to go through all of the major gravitational wave signal components that we know and discuss a little bit how they relate to the physics of core collapse supernova fluid dynamics, and perhaps also highlight the ones that to maybe some people in the audience may not have, maybe a bit less familiar. Yeah. Now, very broadly speaking, why do gravitational waves arise in core collapse supernovae? Well, the basic answer lies in the Einstein quadrupole formula. The Einstein quadrupole formula says you get a strain that is related to the second time derivative of the mass quadrupole moment. And if you have non-spherical flow, and you've seen, I've told you about many examples of non-spherical flow in core collapse supernovae in the first half, then you will get that non-vanishing second derivative of the mass quadrupole moment. What does that probe physically? Well, physically, if you work that out simply by dimensional analysis, is, well, the gravitational wave strain is going to be tied to how much mass you've involved in those aspherical motion, where it's sitting, at what frequency it's moving, and the overall degree of asymmetry. Now, in the core collapse supernova context, we are, of course, this is why we haven't detected them yet in gravitational waves. We are in the less fortunate situation compared to, say, neutron star mergers, that the aspherical motions that are involved, they are, let's say they don't carry the bulk of the energy of the system, right? So the energy that's liberated during collapse of the order of 10 to the 53 ergs, several 10 to the 53 ergs, only a small fraction of that actually goes at some stage or another into aspherical motions that drives gravitational wave emission. Yeah, but they're nonetheless substantial. And you can basically, I will divide the kinds of phenomena that make gravitational waves basically in two classes. That's something else that will be tagged on at the end, which is related to the neutrinos. It can be that you have, and that's the oldest scenario that has been investigated the most thoroughly, perhaps. You can have a situation where your star is already, you have already deformation, global deformation imprinted on it because it's rotating, and you simply deform it due to the centrifugal forces. And then when you have this thing collapse and rebound, already the bounce will create gravitational waves. That's this oldest feature of the gravitational wave emission, the rotational bounce signal. And rotation can also, of course, play a role on a different level, right? Rotation can give rise to its own kind of instabilities, like the low T over W instability, triaxial deformations that can give rise to gravitational wave emission, whether that's around this bounce phase or closely associated to it, but also later. But what we generically always expect to happen is that the instabilities that are responsible and important in normal explosions, which is convection driven by neutrino heating, convection in the protoneutron star, the standing accretion shock instability, if it occurs, will generically make gravitational waves. The reason why we have to emphasize, I think in talking about supernovae as a potential object for gravitational wave discovery, we always have to emphasize both ends because, well, of course, you have a once in a century, or perhaps hopefully slightly more than once in a century chance of detecting a supernova. So the most likely outcome is that it's something that's rather ordinary, and that also means in terms of stellar evolution behind the progenitor, we probably believe that the stellar rotation rate prior to collapse will be rather slow because there's lots of observational indications pointing to efficient angular momentum transport within stellar interiors. So for that reason, this bounce signal or other rotational signatures that may be interesting and may be very powerful, we may not see them. But you still want to consider those cases, of course, as, let's say, the extremely lucky scenario that you might encounter. We all know that discoveries that we encounter very often, they do involve lucky scenarios. The rates of the neutron star mergers, as we followed them, indicate that with the GW170817, we were extremely lucky. So why shouldn't we be at some point extremely lucky with a core collapse supernova? And it might tell us something that's a bit not just the ordinary, but a bit out of the ordinary. All right, but let's go through the signal components, and I'll go through all of them, even if some of them have been studied for decades, and also revise very briefly what we know about them. So the bounce signal, I've explained that. The situation is you need to have a relatively rapidly rotating core already for this to be of some significance. So you're talking about pre-collapse time rotation rates, core rotation rates in the second range, not much more for this to be of any interest. And then what happens is, well, you have the rotational deformation, and then you get the rebound of the core, and as the core is deformed, this will create a gravitational wave signal. Effectively, what that amounts to, it's according to the analysis done by Fuller many years ago, it's effectively the fun that you have a one-time ringing or ringing and then very quick ring down of the of what is at this early point the fundamental mode of this young proto-neutron star inner core of the former inner iron core, which has an interesting feature in that it is a relatively robust signal in terms of having an almost universal waveform template. There's perhaps a slight dependence of the actual frequency on the degree of rotation if you start to rotate very fast. And if you start to rotate extremely fast, then the signal will eventually be somewhat modified. But the interesting thing about it, it's basically a more or less universal waveform, and you can parameterize its amplitude in terms of relevant parameters, like the overall degree of rotational energy versus potential energy before bounce, and maybe the degree of differential rotation that you have in the core. And then you can think about actually measuring that. And the studies that were done many years ago by different groups indicate that this is actually somewhat measurable. If you're lucky and if you have this very fast rotation prior to collapse, it's something that with present instruments gives you a horizon distance of about, well, throughout the entire Milky Way. And it's a nicely templatable signal, which in principle allows for quantitative measurements of things like pre-collapse angular momentum or rotational energy. Yeah. Now, currently, of course, the question about that may be how you can optimize that more, how you can push detection and inference methods a little more just to get this information a little better in the event of a galactic supernova. But that's not my field. That's something that will maybe be covered more by the gravitational wave detection talks. But the physics of that is more or less worked out. Right. Now let's go to what we expect to happen generically, even without rotation in the garden variety core collapse supernova, the typical template of signal components. Yeah, so that corresponds effectively to those phases of the dynamical evolution that I explained to you in the first part of the talk, right? So the first thing dynamically that you see is prompt convective overturn. And the prompt convective overturn then in many simulations, maybe not all of them, also results in a signal component. Very often, though, that doesn't look like it's just a stochastic thing. It looks like it actually has also a definite frequency structure, and you'll see that. I'll analyze that for you in one of the next slides. This is just for you to really be walked through the various phases. Yeah. So this first phase where something multidimensional happens right after bounce, that may give rise to a signal component. Yeah, you see that up here, both in the amplitude plot as well as here in the wavelet spectrogram. Yeah, then typically until the heating region truly forms and until either convection or the standing accretion shock instability grows, you may go through a phase for tens of milliseconds, 100 milliseconds, that is a bit more quiet in gravitational waves. And then once the convective flow especially really kicks off, you get bigger amplitudes again. The amplitudes often tend to peak around the time when the explosion sets in. And then after the explosion, they die down a bit more. And after the explosion, you might get this growing offset in the amplitude here, which is called the tail signal. Yep. Now, the top graph doesn't show you the detailed information of single cycles of this wave signal. And it may not look very ordered, but again, this is something that we now have known for over a decade. The signal actually has quite a definite time frequency structure. So there are definite modes of emission that you see with often relatively narrowly defined emission frequencies. So the most robust and typically most prominent component is one of a rising signal from about 200 hertz, typically to 1,000 or even more. What that depends on, we'll get into that later. Effectively, I'll give that away. What's involved there is certainly some neutron star oscillation mode with buoyancy as the restoring force. The exact interpretation and how it's excited, that is something that we'll look into. Then, as a hydrodynamic instability that also has a very definite narrow frequency associated with it, the standing accretion shock instability can also be reflected in the gravitational wave emission. That will live at lower frequencies, typically between 100 and 200 hertz. How its strength varies and how its frequency trajectory varies, again, that's something that will be covered in one of the following slides. This is just for you to get an overview of the components that are typically present in the predicted supernova gravitational wave signals. There will be a few others. I'll go into that as well. And I think just to convey the understanding by the modeling community is that these features are also relatively robust between all the different codes that are used in the community. We may not agree on exactly where the frequencies are. We may have some systematic differences there, but the qualitative structure of the supernova gravitational wave signal, that's, I think, something that we can communicate as being quite converged, and the add-ons, what the add-ons might be, we'll discuss that in the rest of the talk. Now, of course, one of the things that we also need to do in order to make sense of such a signal, if God willing, we are able with maybe third-generation instruments to not only say that a supernova happened in gravitational waves, but to see something of a real spectrogram. What we want to make of that is, of course, we want to extract some physics from it. Yeah, and in recent years, despite the fact that this is not simulations, I think it's still important to emphasize that many people in the community have done great work in putting the tools together to analyze the time frequency structure of the signal and explain it by means of linear perturbation theory, right? So doing what is known as proto-neutron star astroseismology, so effectively solving the linearized equation for a perturbed supernova core with non-radial perturbations. It's for gravitational waves, of course, it's the quadrupole perturbations that matter. That gives rise to coupled linear equations for the radial and transverse perturbative motions of the fluid, which leads to an eigenvalue problem, and then you can solve that eigenvalue problem. It will result in a discrete spectrum of eigenvalues, and that is something that you can then match to the structures that you're seeing in the spectrograms, and that will tell you about the nature of the underlying oscillation modes. Of course, to some degree, you can also already do what some of us have started many years ago, which is to use the kind of asymptotic local version of this linear perturbation theory and work out sort of what kind of typical oscillation frequencies you would expect from oscillation modes that live in a certain region, your neutron star surface, or inside the gain region as SASI waves traveling back and forth, or in the proto-neutron star core. Yeah, and that's also to some degree always still useful to remind yourself of, because the complicated linear perturbation equations, they may not immediately tell you about the scaling with relevant physical parameters. And when you consider a classical problem like the classical astroseismology, the astroseismological observers that use photon observations, they will often still resort not on a detailed calculation of eigenmodes. Well, they can do that if they have the entire spectrum of eigenmodes to constrain everything. But when you have just one or two modes measured, you may need to resort to simpler scaling relations to actually tie that to the physics that you want to infer from any observed observations. And with gravitational waves, I think it's likely not going to be very different. I would also like to add that there are some avoidable misunderstandings that sometimes come up in the context of when we're discussing the kind of underlying physical modes behind the signals, the components in our predicted gravitational wave signals, and that the linear perturbation theory also has some limitations which then need to be complemented by simulations and by other kinds of analysis. So when we're talking about the linear perturbation theory, we have to, I think everyone who's doing that has to acknowledge that the choice of the outer boundary conditions is actually a very non-trivial issue, right? Do you put your outer boundary condition at the surface of the neutron star? Do you put it at the shock surface? And then do you say you have zero perturbations at the shock? Or do you have something more realistic where you tie that to the actual jump conditions at the shock? Then it becomes extremely complicated. And if you take all of these complexities into account, then sometimes the interpretation of linear perturbation theory becomes a little challenging. That's, I think, what we also need to remind ourselves of. Another thing that also comes about, and this is something that I just wanted to get out of the way, is that when you classify modes and give them names like F mode or 1G2 or 2G2 mode or so, the classification schemes for the modes as classified into oscillation modes where the restoring force is buoyancy, or oscillation modes where the restoring force is pressure. There are some different classification schemes, and there are some, I think, discussions in the literature that can simply be avoided if we're just calling things by a slightly different name because we are using a slightly different convention for labeling our modes. Yeah. So linear perturbation theory, also when you try to fit spectrograms to very high accuracy, will have other, let's say, limitations. The assumption underlying linear perturbation theory of adiabatic perturbations will not be valid outside the neutron star, for example. You will get damping in the neutron star surface region already. That will have also some little impact on your frequencies. So we always, the linear perturbation theory and the tools that are now available to do it, they're really great. We also just need to be mindful of that it also needs to be complemented by other analysis. Now into the individual gravitational wave feature of the predicted signals. As I said, the first instance that for non-rotating collapse, we will see some non-spherical flow is the prompt convective overturn. The prompt convective overturn is sometimes reflected in the gravitational wave signal. And here it's not necessary so much that you see this prompt convective overturn, but at least in the models that we did back at this time in 2012, it's rather that, well, you get some convective overturn that mixes the region behind your shock, and then effectively your shock still does some kind of ringing. I think it's effectively somewhat something of a manifestation of the standing accretion shock instability at early times. And then what you're sensitive to are really pressure waves, acoustic wave traveling between the neutron star and the surface that give rise to a relatively well-defined and quasi-periodic frequency here. I bring up the signal from prompt convection because I actually got a question about that before this conference. And one thing that I think has never been discussed in the literature, but I think I should just tell people, is that this prompt convection signal, or the dynamics of prompt convection, and then the gravitational waves that come out, that is something that I think we need to be very careful about, because here, as I said, making a statement that I made in the previous part of my talk, here it matters how you treat your neutrino transport during the time of the shock breakout, when the shock gets into the neutrino transparent medium. Here it matters to some degree whether you do your simulations in full relativity or not. Yeah? So something like the prompt convection signal, if you're after that, the details of the simulations will actually matter very much. And if that's something that really interests the gravitational wave astronomers, then actually there need to be more simulations of that phase. Those aren't happening by themselves simply because, well, from the perspective of the modeler, who's mostly concerned about why these things explode, this might not be the most obvious thing for us to do, right? But very often in the gravitational wave signal, you will find that, well, you as gravitational wave astronomers might have questions about how robust this signal is that we simply may not have answered yet, because the way of thinking in the core collapse supernova community is just focusing on other things. And the prompt convection signal is just one example for that. Right. Now about this high frequency signal, the growing high frequency signal that's very prominent in the spectrograms. Yeah, so it's an ongoing question of how it works precisely. Yeah, that will come up in the next few slides. But at the most basic level, I think we understand roughly what's involved. You have this region at the neutron star surface, the cooling region, which is stabilized against convection. And that means it can execute oscillations with buoyancy as the restoring force. Yeah. And those oscillations have to be kicked off. They can be kicked off because you have motions, plumes inside the neutron star that are bouncing against this stable region, and you have plumes outside of the neutron star in the heating region that can bounce against this region, and that will induce ringing of the surface region with its characteristic frequency or frequencies. So you can, in principle, of course, excite more than one mode. Yeah. All right. If you just do, let's say, this local analysis of what the typical frequency for buoyancy-driven oscillations in this region is, you come up with this formula that we derived in 2012, which I think is still useful because it highlights the physical parameters that impact where this frequency lives. Yeah, so it's effectively related to the neutron star surface gravity. It's related to the inverse square root of the neutron star temperature. You can note that a measurable proxy for that may be the neutrino temperature of electron antineutrinos. And there are some relativistic effects in this environment. So the gravitational redshift, but also some genuine relativistic effects on the hydrodynamics that you actually have to factor into account. And that sort of shifts this frequency to some degree. That's a non-negligible effect. So despite the fact that the compaction of neutron stars is only of order 0.1, 0.15, for the precise gravitational wave frequency predictions, the GR effects actually do really matter here. Yeah. So I alluded to the fact that there are sometimes some disputes about how exactly this mode is to be classified in this terminology of linear perturbation theory, whether it's a fundamental mode, no nodes, or whether it's a G mode with, genuinely more than one node and driven by or with buoyancy as the restoring force. Well, the number of nodes is not something that's necessarily in dispute, but the precise terminology of how we name it, and especially in conjunction with the various uncertainties in linear perturbation analysis about boundary conditions and so on, may sometimes give rise to simply different terminology. And of course, it may also be true that depending on the slightly different dynamics that we see in simulations of different groups, we actually have a mode that is of slightly different character in terms of, let's say, where the actual nodes of the mode eigenfunction sit and where it sits in the classification scheme. Yeah. All right. So as I said, though, it's important to remember when you're after very precise information, let's say on the 10% level or less and on the frequency of that mode, then details of your simulations will matter. The relativistic treatment will matter. Also, monopole gravity versus truly multidimensional gravity, which is something that's not included in all simulations, matters to some degree. Yeah. So that is something that I think under ideal circumstances we would actually control for, and something that the user certainly has to bear in mind. And perhaps we, in building or in extending our gravitational waveform databases, this is something that we should also try and find ways to clarify really what's the metadata that actually the gravitational wave astronomer wants to see in order to tell, am I comparing waveforms with the same physics or am I comparing apples with oranges? Yeah, so I'm just highlighting this tiny little traps that may not be mentioned in every paper, about where, yeah, you can have a 5% here, a 10% effect here, and where you should actually talk, where as a gravitational wave astronomer, you should actually talk to a modeler in order to know what data you're really getting, what predictions you're really getting. Right. Now, the interesting thing about this high frequency signal is you can already tell from this relatively simple fitting formula that this is something that promises to yield some information about proto-neutron star structure, right? If you use that formula of mine, and if you believe that it works well, of course, you would need information on the neutron star surface temperature from neutrinos. The interpretation of the neutrino signal, again, is not quite straightforward and has some complications because you can have flavor conversion. So you may not get all too reliable information on the surface temperature here. Yeah, but if you had it, you would basically constrain these other terms here, right? So that tells you something about bulk neutron star properties, mass and radius for a warm neutron star, which gives you completely complementary and different information than information on radii of a cold neutron star or something that happens in a neutron star merger, because the radial evolution of the warm neutron stars in cold collapse supernovae is sensitive to somewhat different nuclear parameters. So for example, the neutron star contraction, the radius of the warm neutron stars will be sensitive to the effective nucleon mass. So if you measure that, you're probing slightly different aspects really of the nuclear physics, plus also, of course, of the accretion flow onto the neutron star that also dictates its mass and radius than you have in other astrophysical contexts where you measure neutron star masses and radii. All right. And the fact that we would, of course, like to have very precise or very easily usable information on the frequencies in terms of the neutron star parameters to then go back from the frequencies to those parameters has led in recent years to many of us in the community trying to see whether we can find more of these simple fitting relations for the mode frequencies, perhaps even independent of information that relies on neutrinos to get temperature information. And surprisingly, or perhaps not so surprisingly, the scalings of these various modes can be calibrated to quite decent accuracy with certain parameters of the neutron star mass and radius, or the mass enclosed by the entire shock surface and the shock radius. And I think this remains an active area of research. There's always the risk that you are forgetting, perhaps, or we are forgetting some confounding parameters that might make these universal relations that give us mode frequencies for this high frequency signal, or perhaps other modes. Yeah, the high frequency signal is the most important one to us. That might perhaps make these relations a bit less universal than we would like. And then the question that we have to ask ourselves is, can we perhaps still incorporate that? Can we figure out when that is the case, when we need to be careful? But let's say if you remain within the context of non-rotating collapse, and if you maintain within the parameter space of equation of states that people have studied to sort of calibrate these relations, then this is something that the gravitational wave astronomy community could look at to use to potentially infer physical parameters of neutron stars in the event of a galactic supernova, and perhaps even make that a time-dependent measurement. I'll get to that very, very briefly at the end to sort of prepare the stage for the lecture tomorrow. All right. Now, what is the source of that high-frequency emission? I think, to be fair, we should say that the source of that emission is a delicate issue. So what's driving that? Is it the fact that you have convection in the gain region sort of disturbing the surface region, or is it the protoneutron star convection that interacts with it from below? That's something that's quite tricky to analyze. We'll hear actually a talk about that, I think, today. And there are various means to approach that problem. I think no single one of them is sufficient. You can sort of try to decompose the quadrupole formula to pin down where the waves are actually coming from. You can use energy arguments. You can use correlations between which flow phenomena are active in your simulations and when you emit the gravitational waves. There are various ways to do that, really. Yeah. So decomposition of where the waves are coming from. Tony's group has, so this is something that we've also tried back many years with Håkon Andersen. Tony's group has recently elaborated that regional analysis of the origin of gravitational, this high frequency signal, a lot more. Yeah. The interpretation of this origin by local analysis is a bit, localized analysis over regions is a bit challenging, because you can have interference effects from the signal components coming from different regions. That's why it needs to be complemented, certainly, by other methods. But it does indicate, I think it always has, even from the studies that we've done with Håkon, that you probably have some role both for the convection from the outside and from the convection in the protoneutron star to sort of kick off that high frequency emission mode with that well-defined frequency. And it might be different during different phases and depend very much on the detailed dynamics of the simulations and the progenitor, and be dependent on assumptions and simulation methods. I think we're actually proceeding a bit further in that recently, because the simulations, or some simulations, especially in spherical symmetry, are now so mature that you can effectively go to do a time-space frequency analysis and really try to extract your eigenmodes almost directly from the simulation and see where emissions are coming from. So this is work that my former student Pia Jacobus managed to do, for example, when we discovered another signal component, and Juhai Shah has also been working on it. So pinning down, we're really making progress in pinning down what the sources of emissions are and what the modes are, and can directly interlink the linear analysis and the 3D simulations. Yeah. Despite that fact, the actual origin of this high frequency emission, as I said, is maybe of a mixed character, right? So there may be different sources driving this high frequency emission. If you consider the energetics, how effectively you can excite buoyancy-driven oscillations by convective plumes from above or from within the neutron star, that does suggest scaling relations with the convective energy outside the neutron star that seem to fit well. But the trouble with these kinds of energetic consideration, how effectively can you excite motions in the neutron star surface region from the outside or inside? The trouble is, it really works either way. The numbers aren't so bad that you couldn't make this work either way and accommodate the neutrons, accommodate the signal strength that are predicted by simulations, both by excitation from the outside or from the inside. Why do I nevertheless dwell so much on the origin of that high frequency signal? Well, it's again because the frequency is something that's just set by the neutron star structure, but the amplitude also will tell you something. The energy in gravitational waves in that mode will tell you something. And the question is, what physics does that constrain? Does that constrain the strength of your protoneutron star convection, or does that constrain the strength of the convection outside of the in the gain region, as, for example, the Princeton group is advocating very much? Yeah. I'll skip the temporal correlations again. I think the upshot is just that there may be different ways of exciting that signal. It may be both the proton-neutron star convection and the convection in the gain region. Now, in the last few minutes, about a few other signal components. It's not just this one signal component that we can hope to measure. If we're lucky, and let's hope we're lucky, we might see others. So what, again, my former PhD student Pierre Jacobus comes up here. What we found recently, caveat, only 2D simulations, was that under certain conditions and with certain equations of state, you might actually get some light level of G modes, buoyancy-driven modes, in the interior, in the neutron star core. That would have a slightly different frequency trajectory going down like this. And the interesting thing is that this can potentially constrain, albeit in a very complicated way, and we haven't found any ways to really study this more and make this simpler, to constrain properties of neutron star matter at densities above saturation density. Yeah? And there it becomes really interesting because you have potentially a second handle on directly on nuclear physics from the supernova gravitational wave signal. A little bit on the phenomenology of the progenitor dependence of the overall gravitational wave emission. I think what had already started to emerge with 2D simulations still stands in 3D simulations, although there aren't many big sets around yet, just the one by Princeton and maybe the one that we haven't organized them as well. But the overall trend is still that overall gravitational wave power should scale, should get higher if you go to higher mass progenitors, bigger cores, provided that they still explode. Yeah. Caveats about this high frequency signal. Something I think that needs to be researched more is what are the confounders that could skew this trajectory? And there haven't been too many studies that investigated the influence of rotation and magnetic fields on this signal component. But what we've seen in a few models is that if you have fast rotation, you will have to be careful about mode relations and mode frequencies for this high frequency signal because they will be skewed. This is simply a fact that if you have strong angular momentum gradients, they will modify the typical frequencies for buoyancy-driven oscillations. So we need to also think about a way to combine the information that we have perhaps on rotation in core collapse supernovae from future measurements with how we're using this part of the signal, this high frequency signal, to constrain physics, right? So these are some different pieces of the gravitational wave theory of core collapse supernovae that actually need to be put together for us to, as the two communities, to come up with reliable inference of parameters in the event of a galactic supernova. Some other signal components. Yes, the SASE. You already saw it present in this template that I showed you at the beginning. Oh, not SASE yet. Fast rotation might do things. Fast rotation could give rise to triaxial instabilities that would give us signals that are much stronger than what we see in these normal ones. Yeah, the question, of course, is where do we see these in any progenitors? We'd have to be very lucky for them to rotate that fast. And in some cases, the SASE might also give rise to a strong signal. Has been seen in that strength, I think, only in the simulations by Kuroda. So the conditions, I think, are maybe a bit vague, but I think what you need is you need a non-exploding model where the SASE can stick around for a long time. And perhaps also a very compact neutron star, massive neutron star might help. We also tend to see a bit more of the SASE in models that go to black hole formation and develop very massive neutron stars. So that's potentially interesting, especially if you can integrate over longer cycles. And the information that this would potentially give you is something about, well, the time scale for the SASE oscillations, and that's really set by the shock radius. So if you can measure that, you get information on the shock radius, ideally time-dependent one. Although there is also one caveat here, which is that there can be, I think we have never fully investigated and understood where there are issues of perhaps things like frequency doubling over the base frequency of the SASE that may complicate the identification of this low frequency signal with any shock oscillation frequencies. So there's some very interesting physics to be found here, but you'd actually need to invest a lot more into this to really give the gravitational wave astronomers a definite answer. I want to wind up as the last piece. The last piece of information that you could get is actually in a completely different area of the spectrum. Yeah. So at very low frequencies, we've known for a long time, since the 70s actually, end of the 70s, that if you emit the neutrinos anisotropically, you will also get a gravitational wave signal associated with it, a kind of gravitational wave memory. And an asymmetric propagation of the shock actually has a similar effect. Again, we've known that for a long time. Many of us have written about that in our papers for a long time. The reason, though, why we have never delved into that so much really was that, well, by that time, everyone was just talking about the detectors in the 10 hertz to 1 kilohertz range. So whether you can see any such very slow modulation of the gravitational waveform wasn't a very urgent matter to address. But this is changing a little bit now that we're also thinking about detectors at lower frequencies than what we have with LIGO, Virgo, CAGRA. And for that purpose, this low frequency signal may become of greater interest. But you see, there is actually a huge challenge here, because if you want to have waveforms that tell you what you could learn from that in whatever, the SIGO, the waveforms are actually way too short, right? We'd need seconds of simulations to give you anything that's really useful and not just contaminated by edge effects. All right. And during the very later stage of the supernova, actually, there are also less talked about signal components that might tell you something interesting, which is, for example, that, well, things like dynamos during the proton-neutron star phase, they could give rise to an extra gravitational wave components at relatively low frequencies, and potentially help you constrain with gravitational wave what's going on magnetohydrodynamically in the interiors of neutron stars. That's work by Jérôme Guillet's group in Paris. And with that, I think I'll skip the caveats. With that, I conclude that, you know, there are always caveats and things that can go wrong in the gravitational wave signals that we sell you as supernova modelers. But I would just conclude by saying, we're in simulators, we're in a state where we can actually provide at least very many waveforms that allow some meaningful experiments, some meaningful research with gravitational wave classification and inference techniques. That's not the subject of today's talk, but I think that's just a good way to conclude this particular lecture by making a good connection to the talk that awaits us tomorrow, and say we're at a position where we can provide the gravitational wave community with something that they can feed into their pipelines and not just a few signals. Really useful stuff. Yeah? And even perhaps do some time-dependent inference of neutron star parameters. And I think that's what we should be thinking about, right? Maximize the science potential, not be content just with claiming, yeah, there's a galactic supernova and we've also seen it. All right.
Thank you, Bernhard, for once again doing the impossible. Tomas, if you wanted to come down, I think you're up next, right, Tomas? Yeah, come on down. We have time for, really don't, but we'll take one quick question. Jade, I'm not going to pick you because. Is there a question? A pressing question? See, everybody's afraid of you, Jade. Go ahead.
So I saw some gravitational wave signals where the prompt convection was much higher amplitude than the rest of the signal. And I found that worrying because if we had gravitational waves from supernova and we only saw the prompt convection, it would be like the same frequency and duration as like the GW 231123 that we saw last week. And everyone would say it's binary black hole. So I wanted to know how realistic you think it could be that prompt convection could be that loud.
My gut feeling, although that ought to be backed up by simulations and by good comparisons, is that the signals that give you a huge prompt convection signal, they probably do the prompt convection phase worse physically than the ones that give you less. Yeah, I think it's probably some rather, I wouldn't say artifact in the simulations, but it's the models with the best neutrino physics and transport for that phase, I think, give you less of a prompt convection signal. That's, I think, a fair statement.
So the details matter. Okay, so we're going to